Okay, so ladies and gentlemen, good afternoon. My name is Ahmed Innawi. I will be moderating today's webinars. Let me add my welcome to everyone. It's my pleasure to introduce our speakers. We have two speakers, Dr. Greg Smestad and Dr. Leonardo Micheli. Dr. Greg Smith, I will talk about the basic physics of soiling in solar power plant, followed by Dr. Leonardo. He will talk about advanced simulation and mitigation of photovoltaic soiling. Doctors, I know Greg Smith since long time, since 1992. In Berlin at the Hahn-Meitner Institute. We worked together. He's graduated with a PhD from the Swiss Federal Institute of Technology in 1994. He received before his master's degree in material science and engineering in 1985 from Stanford University, and his bachelor in biology in 1983 from the University of Santa Clara, California. In Berlin, we conducted together research, and I learned a lot from him regarding dye sensitization, solar cell, and optoelectronic, and many lab tools like spectral response, how to build up the setup at the time. So I learned a lot. Before he moved to Paul Scher Institute in Switzerland to conduct his PhD with collaboration with Professor Gretzel in Lausanne, I guess. He was employed before and he got a lot of skill in Leverance National Laboratory from 1995 to 2002. He was professor in California State University, Monterey Bay, and then at Monterey Institute of International Study. He's currently working on optoelectronic and solar cell as consultant, and he served before as editor for solar energy material and solar cell from 1990 to 2016. So we have in front of us an expert with more than 20 years experience. And I would like to thank him for coming and giving us this lecture on soiling. Dr. Greg Smith, the floor is yours. Please open the micro.
Here we are. Have to hit the right buttons, don't I? So thank you very much. I will try to do my best to look at the basics of soiling in the solar power plants. And
Please
then my colleague.
The full screen.
Yes, the full screen. Here we are, full screen. My colleague and friend Leonardo Micheli will take it when I finish to look at the practical aspects, but here are the basics. First of all, what is soiling? We have ambient particles in the atmosphere that are deposited. We call this particulate matter, PM, and it reduces the transmission on the photovoltaic installation or on a CSP system. So I give you an overview. I talk about what the soiling ratio is. We talk about this in terms of then the optics, the light scattering, the wavelength dependence, the angstrom turbidity equation, which can help to describe the wavelength dependence, and model versus experiments in the context of soiling mainly in PV, but again, remember that this happens in concentrating solar power plants, CSP as well on the mirrors. So any surface. So first of all, I mentioned particulate matter. We measure this typically in micrograms per cubic meter in the atmosphere. And this then is PM10, particles that are less than 10 microns. This is dust stirred up by vehicles or roads or agriculture, winds. We also have PM 2.5, which is less than 2.5 microns from wood burning, forest fires, agricultural, other industrial processes. And these are quantities that describe the particles in the atmosphere. Of course, they have health implications. And so the various environmental protection agencies in individual regions and for the World Meteorological Organization, they study these for many different reasons. We study them because these particles deposit not only in our lungs or on buildings, but also on solar panels and CSP. So here's my cousin David Bernal's system in Los Angeles. You could see what soiling looks like, very irregular on a photovoltaic plant. That was crystalline silicon. This is a Marcus Beck's system in the mountains here in California. You can have bird droppings. You can have dust on cadmium telluride thin film PV module. So this, you could imagine, reduces the output of these devices. So what is soiling in terms of a definition? This is the accumulation of dust, dirt, and particles on the surface of PV modules or on CSP mirrors, I will keep saying. So the drop in power output, especially in places like the Middle East or in deserts, can be greater than 50%. So it's a significant output, which represents loss of both power and revenue. The drop in energy yield in the US, even in the US, can be anywhere between 0 and 6%, but in other regions, it can be much higher. So what will scatter light? My colleague, Thomas Germer at the National Institute of Standards and Technology, he has a course that you can look at online. You can search for that, but we can have roughness, scattering light, we can have particles, we can have particles of different shapes, film residues, and that is what soiling is, all of these things put together. So how do we characterize soiling for a photovoltaic system? We need to look at the quantum efficiency, which is called the EQE, or external quantum efficiency, which can also be translated very easily mathematically to what's called the spectral response. This tells you the response of the solar cell as a function of wavelength. Then we need the incident solar spectrum, which we could give many symbols, but here we can call it E. We can look at the soiling ratio, which we will talk about. And then the angstrom turbidity equation, which is usually applied to the atmosphere itself, but we applied it to the very thin layer of soiling on a solar panel. So we're applying a concept which was just used in the atmosphere for these particles, but we can also talk about it in terms of the solid state when these particles are deposited as a film. We modified the formula, the angstrom turbidity equation, to do this new thing. And then we can fit it to the data. Okay, so first thing you need to do to understand soiling is you need the case where everything is fine and ideal. For this, you need to know something about solar cells. They have a response, a quantum efficiency, which is the number of electrons that you get out versus the number of photons that are coming in, thus quantum. It's an object divided by another object, electron and photon. So the spectral response with a little bit of mathematical manipulation, Q times the wavelength, the Planck's constant, and the velocity of light, we can translate the spectral response and the EQE. They're really the same concept. If we want the short circuit current for a solar cell, we take that spectral response and we multiply it by the spectrum that you see down here at the bottom. This is the solar spectrum under different conditions. So already the light can be filtered through the atmosphere by particles. And that's described by the normal angstrom equation. But in order to get the ideal case without any soiling deposits for the current produced by a solar cell, you take the spectral response or the quantum efficiency, you multiply it at each wavelength by the incident light, and you integrate. And that's been well known. You can see this through many different platforms. And this spectral response is different depending upon the technology. Monocrystalline silicon, gallium arsenide, cad telluride, copper-indium gallium selenide, which Ahmed and I were working on this related materials years ago at the Han Meitner Institute. So different solar cell technologies have different spectral response. They have different response to the incident light. And then we can add this thing called the soiling ratio to the ideal case that I just showed you. Now, the soiling ratio is the short circuit current when you have a soiled case versus the reference case, the ideal case, where everything is clean on the solar panel. And there's a standard, an IEC standard, which expresses this ratio and talks about how it can be measured, how it can be, what conditions it can be measured on. So this is, of course, a function of time. And we call this a time series when we look at the soiling ratio as a function of time. And I believe that Leonardo Micheli will talk a little bit about these. So each one of these currents here, we can talk about the current density, and this I becomes a J. It's the same thing. Yes, please put the questions, any questions in the chat, I see. So you have this integral that I already told you about. In the case where you have a soiled, then you can talk about this transmission. And the transmission, is limited by both the transmission of a glass cover or a dirty glass cover. And so this soiling ratio becomes this ratio between something that has a transmission that's not 1, 0 to 1, 0 if it's opaque, 1 if it's ideal, and then we integrate the spectrum and the spectral response, or the quantum efficiency. And then the reference case, of course, is ideal. The transmission is 1, it's ideal. So we can do this. Leonardo and I put these together for the soiling ratio for amorphous silicon on the right and monocrystalline silicon on the left. And we could look at these aspects of this equation. We can have the irradiance in one case, which might be one time of the day, a blue rich, for instance, at noon, where there's very little losses from the atmosphere itself, or red rich at the morning or at sunset. And we can look for monocrystalline silicon here on the left side, and the quantum efficiency or the spectral response here. And we can integrate, multiply and integrate those two, and get the final soiling losses across some kind of broadband system. We can do the same for amorphous silicon. And this, again, this integral is represented by this shaded area. What's not shown here is the transmission as a function of wavelength, but we'll show you a little bit more about that. The point of showing you this is that the same light blue spectrum here, when you have a quantum efficiency that's this dark blue versus the spectral response, or this red curve, can be different depending upon the technology. Amorphous silicon is different than monocrystalline silicon, and both of them are different than cadmium telluride. Soiling depends upon the spectrum of the incoming light. Okay, so here we do show this transmission. And the thing that you should take away, this light blue line, so you first notice this, this quantum efficiency curve, or the spectral response here. It's a dotted line, spectral response or quantum efficiency. You see the standard solar spectrum here in green here. And then you have the relative hemispherical transmission, which again is the transmission of the glass cover soiled versus the reference, which is clean. So you see here as a takeaway that soiling produces something that has more losses in the blue. This is the blue region here than it does at the red. It always seems to have this tendency of having this kind of curve. And this is also a curve that we see when we're looking at the transmission of the atmosphere itself, because when those particles are in the atmosphere, they do the same thing. So that's why we applied an equation to describe this, which I'll talk to you about. And this could be found in this open source article, Scientific Reports in 2020. You can type our names in and you can find some of these curves. Here we have an experimental curve from Chennai in India versus here where I live in San Jose. And you can see that these three components of what I showed you before that are multiplied together are different depending upon where you are and how much soiling that you have. Okay, so soiling has different types. We have Rayleigh scattering and we have Mee scattering. You can find this in a very nice book. I think it's also open source, Introduction to Solar Radiation by Muhammad Iqbal, Academic Press, 1983. And he describes the shape of these curves, of course, again, in the atmosphere. And what I did is I took inspiration from Dr. Iqbal's work, and I said, well, these same particles are the ones that are being deposited. So we can think about this in terms of the same kind of mathematics that he shows in this book. And the type of scattering is called Mee scattering, M-I-E. Okay, so the angstrom turbidity equation, mathematically, that you'll find is that the transmission of this due to soiling, the ratio between the clean and dirty is some kind of an exponential, some kind of an index representing the amount of soiling, a beta, and alpha, the wavelength dependence, times some kind of an amount, a thickness. And so alpha is different depending upon the size of the particles and is a wavelength exponent. Generally, this is the range, and this is an optical path length. This is the standard angstrom turbidity equation that you should all know because it describes the transmission, the scattering of the light in the atmosphere due to these particles in the atmosphere at different times. This is a function of time. Well, you find this equation again in his book, and again, this same kind of gradual shape with blue light being less transmitted through particles than red light. You should take that away with you and know that this is one of the things that you can be tested on, I hope. Okay, so Mee scattering is something that you can study then as part of this. I'm going to shift before I go to Leo to something else here. Again, full screen. I want to talk to you just a little bit about another aspect that you can do again at any lab, the optical microscopy. And there we want to talk about the fact that you could look at the particles under the microscope. No, this isn't the stars at night. This is a picture that we took at 500x through a microscope of the soiling. And we can also look with SEM at the soiling and find some very interesting things. But what I wanted to convey to you is that Leonardo and I found that, at least to first order, this can be described by an existing standard, which has a number here, and some kind of a cleanliness level of the particles deposited on surfaces. And this is a kind of a log normal distribution that's used for clean rooms. And so this is a well-known thing. So we're borrowing from it. And this is the equation for the number of particles as a function of their size, and this parameter, which we call the cleanliness level. Now, we didn't invent this. We're using it. We're borrowing it. Just like we borrowed the angstrom turbidity equation, we're borrowing it and bringing it into the study of soiling. We're applying it. here we're applying an existing standard for the contamination in clean rooms, and we're applying that to the surfaces that we can study by microscopy. So this cumulative number of particles as a function of their size. So we're usually on one of these curves. So for instance, if L has a particular value of something like 1,000, we're on this curve, we can understand the distribution of those particles as a function of their size. There's the one. And so we can obtain a micrograph, analyze the micrograph, count the number of particles, get an equivalent diameter, and plot it in a certain way as applied to this to obtain a cleanliness standard. So here's one from San Jose, and this is the non-log way of plotting what we get experimentally from a microscope. So this is the change in the number of particles as a function of their size. You can see that most of the particles are small particles, and then it tails off. And when we plot this on a log plot, we do get a nice curve. And that's another message that we want to share with you, and to realize that this is also given by a certain standard in industry that is used to do these kinds of particle size distributions. So here, again, experimentally here for San Jose, but it works anywhere in the world to some degree. We see the log of the cumulative number of particles. So we have to add up all the different sizes as a function of the particle size. And so that previous thing that I showed you plots up on a log plot to be fairly good, so that we can, as Leo has done here, show that this is characterized by a single number, 861. And so the area coverage, then, we can also say that 3.3% of the surface is covered by particles. Now, so I've given you two things. I've given you spectroscopy, and I've given you microscopy. And so what you take away then is that there are some basics that one could look at in any lab anywhere in the world, both looking at soiling in terms of the wavelength dependence and also looking at it in terms of the particle size distribution. And with those basics, then I turn you over to Leonardo, who gives you then the implications of soiling from a larger scale, not the microscopic scale, but the larger picture. So I thank you.
Very much, Dr. Greg. I don't know if we have to leave the question until the end. I think it's much better. So I will just briefly introduce Leonardo, and then I give him the floor if you allow me. So let's go. I will, okay. Then they go back to this picture here. So so the Dr. Leonardo Micheli is an assistant professor in sustainable energy at Sapienza University of Rome, Italy. I hope I spelled it very good. He has a PhD in renewable energy awarded in 2015 by the University of Exeter. I just looked to this university in internet, and it's very well ranked. In this in his postdoc, he has been working at the National Renewable Energy Laboratory in the United States, and it's very well known in terms of solar. And at the University of Jaén, Spain, in 2018, he was awarded Marie Sklodowska-Curie Individual Fellowship. And in 2021, he was granted the Rita Levi Montalcini Fellowship by the Italian Ministry of Education, I guess. His research activity includes the monitoring, the analysis, and the prediction of photovoltaic performance and the optimization of loss mitigation strategy. Currently, he is in charge of the Sol for PV project with the aim to map the soiling loss and cleaning recommendation in real time. So I will give him the floor. The floor is yours, Dr. Leonardo, and thank you very much again for helping us in this area of PV study. Thank you.
Thank you so much, Professor Nawit, for for inviting. It's always nice to be here. It's our second time at speaking here, and I'm very happy to be back again. Let me also thank Greg. He always gives very good overview of what soiling is, and even a deeper, he has a very deep knowledge of all the physics behind that. And again, it's very nice to work together also because we come from different perspectives. Greg is a physicist. I'm more an engineer. So I really like to try to, give an application to all the work we do related to soiling. So what today I wanted to present and I'm going to talk to is advances in simulation and mitigation of photovoltaic soiling. So Greg has already done my job easier because has given a pretty nice introduction about soiling. I'm going to repeat some concepts just to make sure that everyone is on the same page. Then I'm going to go into soiling mitigation. So trying to explain in which ways we can limit soiling, reduce losses. And in particular, I'm going to talk about cleaning optimization, which will be one of the main topics of this talk. Soiling, as we will see throughout the talk, is not just a matter, however, of maintenance, of operation and maintenance. It's something that starts even earlier. For example, when a new PV site is selected, we can already act before the PV site is operational to limit the soiling losses. And we will see that. We will talk about how soiling can be estimated, how we are working to map soiling, and then I'm going to take chance to describe some of the ongoing work and try to summarize the conclusions. Very quickly, as Greg said, when we talk about soiling, we meant the deposition of dust particles and surfaces on the surfaces of photovoltaic modules, PV modules. Also concentrating solar power experiences soiling, but I'm going to focus mainly on photovoltaics. So what happens when we have soiling on top of photovoltaic glass? Soiling absorbs and reflects part of the incoming sunlight. So at the end of the day, we have less irradiance that is able to reach the photovoltaic material, and therefore less energy is going to be converted by the PV module. The layer of soiling on top of the PV glass is reducing the amount of energy converted by the photovoltaic modules. And this is causing both an energy loss and an economic loss. With some colleagues some years ago, we estimated that soiling had caused just in 2018 the loss of 3 to 4% of the global energy. Soiling indeed is a worldwide issue. It affects several countries, even countries that we might consider rainy. Such as the UK, in which we expect rain to clean the modules quite often. Well, soiling can be an issue over there, and at a global level, we expect it to cause the loss of 3 to 4% of the global photovoltaic energy. This translated back in 2018 into a loss for the global PV community in the range of 3 to 5 billion euros. At that time, we tried also to predict a bit the future, and we estimated that by this year, the losses would have actually increased. Why? Because we have more and more PV systems that are being installed in areas that have extremely high potential, such as desertic areas, which, however, have yes, a lot of irradiance, but at the same time are very arid and therefore can experience even more soiling losses. And because of this increase, also the economic impact of soiling was expected to increase. And, you know, we're going to touch this topic later on. We didn't take into account how the energy prices have been increasing over the last few years, at least in Europe. And, you know, in higher electricity prices, every kilowatt hour of electricity you do not produce because of the soiling loss is going to cost you more. So probably we underestimated the real losses because we didn't predict such high electricity prices right now. So there are different types of soiling. You know, when we speak to people, they will typically imagine, you know, soiling due to mineral dust, siren storms, for example. However, soiling can have a lot of different shapes, going from bird dropping to organic matter growing on PV modules, down to artificial, you know, emissions, such as emissions due to industrial processes or agricultural activities. So soiling can have different shapes, and that's why it can really take place anywhere, essentially worldwide. However, what makes, at least to me, soiling particularly interesting is that soiling can be is a reversible loss. So differently from several degradation mechanisms, soiling is reversible. So we can take action to correct soiling, to actually remove soiling that has accumulated on the PV module. This is typically done through cleanings. We will see cleanings are the most common soiling mitigation activities, but there are also preventive actions that we can put in place before a PV system is operational to decrease the rate at which soiling will be depositing on the PV module or to facilitate its natural removal. However, as I said, cleanings are still nowadays the most common way to clean a photovoltaic and a CSP system. Cleanings also have different shapes, different technologies can be involved. We can go from fully manual cleaning activities up to fully automatic cleanings, especially in areas that have extreme soiling. Nightly, you know, cleanings might be performed every night, and if that's the case, we might have robots installed directly on the PV strings that makes it possible to clean the PV system every night. So again, also different technologies are available for PV cleanings. However, independently of the technology, there are always costs associated with this type of cleaning. That can be, for example, you know, the cost of the human labor, or can be the cost for the electricity to move the robot, or for example, the cost of fuel for a tractor, or the cost of water need for cleaning. So typically artificial cleaning, you know, manual, any type of cleaning that is made by an operation and maintenance team will come with a cost. So on one side, if we imagine of increasing the number of cleanings we do on a PV system, we can see the energy also increasing, right? The more you clean, the more, the less soiling you will experience, the more energy your system will produce, and therefore the more revenues the PV operator might have. At the same time, however, the more the cleanings, the more the cost you will have. On top of that, we have to take into account that some natural events, such as rainfalls, can wash off soiling from the photovoltaic surface at no cost. And here, you know, is the goal of, you know, some of the research that we are doing. Try to run cleaning optimization. So try to maximize the difference between the profits you can make from cleaning the PV modules and the cleaning cost. Clearly, you want to get the maximum profits and minimize the cost so that, you know, you can maximize the revenues you get from good soiling mitigation activity. How we do that? Typically, we start from photovoltaic power data. So we take the photovoltaic time series coming out of an existing power plant, and by taking into account the efficiency of the modules, the capacity of the system, and the configuration of the system, for example, the tilt and the azimuth angles, we are able to split the lossless energy yield from the actual soiling loss profile. We then feed both these data, both these time series, into our own cleaning optimization model that takes into account the performance degradation of the system, takes into account the electricity price and the cleaning cost, and produces for us a soiling loss estimation as well as a mitigation mitigation plan recommendation, which typically is a recommended cleaning schedule and an expected, cleaning and the expected cleaning profits. So Greg has already mentioned that, but let me again call it back. I might refer in this talk to the soiling ratio, which is a metric that is defined in the IEC standard for photovoltaics. The soiling ratio essentially represents 1 minus the soiling loss. So we have a soiling ratio of 1 when there is no soiling on the modules. So if soiling is not present, we are going to have a soiling ratio of 1, like in all these conditions. You see in all these days. However, while soiling deposits on the PV module surface, the soiling ratios start decreasing while the losses start increasing. So again, the soiling ratio is 1 if we don't have losses, while it is lower than 1 when soiling is present. The first part of the talk will be based on some data we got from Granada. Granada is a city in southern Spain, which makes that particularly interesting for European and probably also MENA, for the MENA region in general. Why? Because it's a city that has quite high energy potential for photovoltaics, because it's quite well, has a very high insolation, and at the same time is extremely interested for soiling. The south of Spain is experiencing periodical dust storms from Sahara, and therefore soiling can be quite intense over there. The site we were given data for is a 1 megawatt site made of monocrystalline silicon modules, exposed essentially at optimal tilt and orientation, 30-degree tilt, southward orientation, and we got both AC and DC data for 2019. So what we did first was eliminate all the losses and the mechanisms that are not directly related with soiling from the PV power data. So we got a normalized DC performance ratio, which we can essentially use to calculate our soiling ratio. Again, we removed all the losses that were not related to soiling, and therefore by using the actual DC performance power, the normalized power ratio, we could actually extract a model soiling ratio, which is here represented in red. As you can see, the site has some rainfalls occurring during winter, while summer is quite long and dry. Most of the losses, as you can see, typically occur in summer. However, there are 2 dates that are of particular interest if you look at this site. First of all, summer starts with not much soiling accumulation. As you can see, there are not much soiling losses until July starts, more or less. So on this day, there is a change at the rate at which soiling starts depositing on the photovoltaic modules. Before, the soiling losses increased by 0.02% per day. After June 22nd, the losses increase at a rate of 0.3% per day. What happens? There is a wind, sand-laden wind coming, from Northern Africa over Granada. And this wind brings dust with it, which slowly deposits on the module. And this is what these data are telling us, right? There is a lot of dust in the air that is slowly depositing on the modules. Also, as I said, there is a second date. There is a cleaning taking place with no rainfalls related with it. Well, that was a cleaning that was done by the local O&M team. However, what we wanted to do in this analysis was to run a cleaning optimization analysis. So we really wanted to understand which was the maximum extent of soiling if no mitigation was put in place. So what we did, we tried to model how the soiling profile would have been if no cleaning was, took place. So essentially what we did, we extended the soiling deposition until the first rainfall at the end of the summer. As you can see, in this case, if soiling is unmitigated, most of the losses, 95% of the losses for this site takes place in summer, which again is the driest period and the period in which the concentration of particles and dust in the air is the highest. Toward the end of the summer, before the first rain of September, losses can be as high as 23%. And over the whole year, the losses are in the range of 3% if we take an average. Now, we have this soiling profile. This is the same soiling profile you see here in green, just with a different scale. And what we did, we ran different cleaning schedules. So we modeled the effect of 1, 2, 3, up to 6 cleanings per year on that same soiling profile. And this is what you see in this lower graph. You see how the soiling profile changes if you run 1 cleaning or if you run up to 3 cleanings. Again, here I'm showing only, soiling loss profiles for scenarios with 0 up to 3 cleanings, but in reality, we modeled up to 6 cleanings per year. Again, when we talk about cleaning optimization, we also have to take into account the economic side, because both soiling has a cost, but also cleaning has a cost. And to do that, we took into account 2 common soiling economic metrics. First of all, we took into account the levelized cost of electricity, the LCOE. This is a metric typically used to compare the cost of producing a kilowatt hour of electricity from any type of energy system. So it is calculated as ratio between the total cost of the system over its lifetime, so installation cost and yearly O&M cost, divided by the total energy that the system produces over its lifetime. So it's expressed as euros or currency in general divided by kilowatt hour. And clearly, since it is a cost, the lower its value, the better. Soiling mainly plays in the O&M cost. Indeed, the cleaning frequency, the cleaning cost, both affect the O&M cost. The more cleanings we have, the higher the yearly O&M cleaning cost. However, as I said earlier, the more cleanings we have, the more energy we are expecting to produce, because the more cleanings we have, the lower probably the soiling losses we are going to experience. On top of that, however, we took into account also a second metric. If you have noticed, the LCOE tells us how much it costs to produce electricity, but is missing a very important parameter, at least for operators and investors, the electricity price. The electricity price, indeed, is essentially a reward for every kilowatt hour of electricity that you produce. And the LCOE does not take into account that. So in order to evaluate how much the electricity price which is the role of the electricity price in soiling mitigation and cleaning optimization, we took into account a second metric. This is known as the net present value, and essentially is a metric that tells us how profitable is an investment. An investment in particular will return a profit if the NPV, the net present value, is greater than 0. If the NPV is lower than 0, then the costs associated with investments are higher than the returns. and the investment is not profitable. Otherwise, if the NPV is greater than 0, we are making a profit out of the investment, and the greater the NPV, the greater the return of the investment. This is calculated essentially as sum of the yearly revenues minus the yearly O&M cost minus the installation cost. And the yearly revenues in this case are calculated by multiplying the yearly energy yield we previously took into account, multiplied by the electricity price. So first of all, we looked at the different scenarios we modeled, and we tried to understand how the LCOE and the NPV varied when, instead of leaving soiling unmitigated, we started cleaning 1 up to 6 times per year. The results are shown here in terms of improvements in economic metrics. An improvement, a positive improvement, means that either the LCOE decreases or the NPV increases. As you can see in both cases, if we clean once per year, we get the highest improvement, both for LCOE and for NPV. So both the metrics actually are optimized if we do for that site at least 1 cleaning per year. However, what is even more interestingly is what happens if we increase the number of cleaning per year. As you can see, the improvement now is negative for LCOE. So if we do 2 or 3 cleaning per year, the LCOE is actually increasing. We are increasing the cost for producing the kilowatt hours of PV energy that we are producing. Despite that, even if the cost of producing electricity is higher, we are still making a profit out of the investment. The NPV is still bigger than the NPV we will get if no cleaning was done. So cleaning more 2 or 3 times is still more profitable than not cleaning at all at this site, but it causes an increase in the cost of producing electricity. So when we want to run cleaning optimization, we really have to understand which is our goal, because different metrics might give us different recommendations. Why that? Because again, the NPV takes into account the electricity price, and the electricity price is an extremely key factor, again, for soiling mitigation. When we ran that analysis, the electricity price in Spain was in the order of 60 euros per megawatt hour, or 0.06 euros per kilowatt hour. It's shown here. So the second metric we have to take into account is the cost of surface cleaning, which in Spain is in the order of 9 cents per meter square. So to clean up a module that is 1 meter square, we need something in the order of 9 cents. What that means that at the time, we would recommend cleaning that site once per year. However, if the electricity price increases, the reward for producing electricity also increases. And therefore, for example, if we had an electricity price of 10 cents per kilowatt hour, we would recommend cleaning that site twice per year rather than 1 in order to maximize the profit. You can apply the same thinking and go up, for example, to 200 euros per kilowatt hour, 20 cents per kilowatt hour. And in that case, you will get that a recommendation for cleaning that same site for 3 times per year. And you see here how electricity price is extremely important for soiling mitigation. And why I'm stressing this out? Because at least in Europe, we have been experiencing some, very unique electricity price trends over at least the last 2 years. As you can see, this is how electricity price behaved in Europe, until at least 2020, 2021. Prices were limited up to a maximum values in the order of 100 euros per megawatt hour. After 2021, We have been living in exceptional times, and the prices in some countries, you can see prices in Italy for electricity have gone as high as 500 euros per megawatt hour, meaning that producing a kilowatt hour of electricity in Italy in 2022 was 10 times more profitable than it was producing it over the past decade. So what that means that over these exceptional times, you become extremely profitable, solving mitigation, loss mitigation. And so owners and operators will be more incentivized to clean. However, we might be living in exceptional times, but several experts agree that prices, by the end of next year or in a couple of years, will go back to historical levels. Even if that appears, however, forecasts are telling us that electricity will become more and more expensive over the upcoming decades. So we will experience an increase in price. Here you see 3 different forecasts. And as you can see, by 2050, the electricity prices will go into will cost, at least again for Europe, in between 60 to 100 euros per megawatt hour, compared to previous decade in which prices were in between 40 to 60 euros per megawatt hour. And what happened, again, if we are experiencing higher electricity prices? Clearly, the profits for owners and operators increases because they get more money for the same kilowatt hour of electricity. However, that high electricity price is an incentive to them to produce more electricity because they have more funding available for cleaning the system, for reducing the losses. So what will happen? They will clean the system more often. And so the system will actually produce even more energy than it would in low price conditions. What that means is that on top of the additional profits due to the higher electricity prices, what we will see in future is that the system will become more and more efficient because stalling will be more and more mitigated, because owners and operators will be rewarded with more energy, with more money for each kilowatt hour of energy they produce. So on top of the higher electricity price that they will be paid, they will be gaining more, even because they will be producing more energy. So the higher electricity price scenarios will provide a double benefit for them. Again, more reward for the energy produced, but at the same time, they will produce more energy because of that reward. And so they will get, again, a double benefit from that scenario. However, stalling is not just an O&M issue. I already mentioned that. I'm going to stress it out again. Indeed, it can start with the site selection and design of the plant, for example. Imagine you have a PV system installed in an area where you don't have paved roads. Every time you have a vehicle running by, it will be suspending dust on your PV system. So you can do some simple stuff like paving the road or, build barriers, planting trees to try to limit the dust that will be transported from the road onto your PV panels. On the other side, some researchers have suggested that, for example, we can change the way tracker works to try to place at night the PV modules in position in which the soiling deposition is limited. You see, these are all activities that are not related with operation and maintenance, are related with the way the PV plant is designed and the PV plant and the site is designed. However, site selection also play a role in soiling loss, clearly. If we know how much losses we are going to experience in a PV site that we are selecting for a new PV system, we can better plan our soil mitigation activities. And this is what I want to show in our next slide. So here you see an example of several PV systems installed in the Bay Area in California. You see, we know all the losses, all the soiling ratio from all these systems. But now we want to install a new system in an area that is nearby these systems, but where we don't have any soiling measurement. So how we can estimate losses in this site if we don't have any specific data from here? Well, yes, we can take information from all these nearby sites. And why I'm showing that? Because it's becoming more and more common to have resources like the NREL soiling map. The NREL soiling map is essentially a website where NREL researchers have gathered information about soiling. Now, this is specific for the US, but you can find similar maps also for worldwide. Are typically discrete data from different somewhere you might the losses that your site is going to experience later on during its lifetime. So you can apply different techniques. Unfortunately, I don't have time to go through all of them, but there are simpler and more complex techniques that make it possible to interpolate data from nearby power plants in order to estimate the losses that your site is likely to experience. However, the most common approach in the industry sector is to use what is known as nearest neighbor approach. In this case, what they would do is that they will estimate that the losses at their new PV site are equal to the losses that the nearest PV site are experiencing. So, for example, this is how the losses at different sites over California will look like if different techniques are applied. Again, you can look at all these techniques. They have different pros and cons, but typically, if you move from a nearest neighbor approach to a simple average or inverse square distance weighted average or the cluster distance estimation, you are increasing your computational effort. So most people try to use the nearest neighbor, and my colleague Matthew Mueller and I really wanted to help the industry, try to providing them with information on how reliable this type of approach is. So what we did was using a geostatistical approach known as semivariance to try to study how the dissimilarity in soiling between two sites changes depending on their distances. So we took all those data from California and we tried to extrapolate a semivariance graph from that site. And essentially the results we got are you can find them here. We can approximate our semivariance to a semi-uncertainty in soiling estimation. And here you can see the distance from the site you want to estimate losses for and the site where you have losses for. As you can see here, the uncertainty or the semivariance tend to increase almost linearly up to a certain distance, at which the semivariance essentially saturates. What this graph is telling us is that you can estimate soiling using a nearest neighbor approach, but you have to accept some uncertainty. And you have to accept that that uncertainty increases at a rate of almost 0.1% per kilometer. So after 10 kilometers, you have an uncertainty that is probably already very close to 1% per kilometer. That keeps increasing until a distance of 60 to 80%. At that point, what happens? You have a semivariance of 4%. And if you remember, the losses we had in California ranged between 0 and 8%. So what that means is that if your nearest neighbor is located at 60 kilometers or more from your site, the uncertainty in soiling estimation is essentially as big as the maximum soiling loss that you might experience. So again, we wanted to give numbers and tools that the industry could use to try to estimate the losses using this very, very simple approach. However, there are other ways that can be used to estimate soiling losses, because we know that soiling is caused by several factors, such as rainfall, such as particulate matter. And we can use soiling estimation model to estimate a soiling loss profile starting from those data. Why would we do that? Because those data are widely available. There are maps telling us how particulate matter is distributed over the globe, and we know how much it rains in several locations worldwide. This is why there are already several models that makes it possible for us to estimate the soiling losses from parameters such as rainfall and particulate matter. So what we did with Greg and other colleagues last year, or maybe 2 years ago, was try to compare the estimation of two models. Now, for this class, it's not very useful to say which models we are using, so we're just going to refer to Model A and Model B. And as you can see, these two models actually return pretty similar qualitative distribution of soiling. Identify that most of the losses in the US are occurring over the Southwest. However, if you look better and you look at the scale, you can see that one model is telling us that in the US, the maximum annual soiling losses are in the order of 3%, while the other model is telling us that the losses are the maximum losses is in the order of 4%. So you see different models, given the same data, are returning us different estimations. So we really need, more comparative studies, more validation studies to really be able to reliably estimate soiling losses from environmental parameters. However, this is not the worst case. Indeed, the situation even worsens if we give to the models different types of data. For example, we can get particulate matter from ground sensors. These are typically present in cities to control their pollution or the air quality in cities. So there are really a huge number of sensors distributed in every country. However, we can also use satellite data derived particulate matter, for example. And the community has been using different models, inputting either satellite-derived data or ground measured data as if they were interchangeable. And what the analysis show us is that if we use Model A with ground measured data, our maximum loss is 2.8%. If we use satellite data instead, we go as high as 7% per year. So there is a factor of 2 between these two maps generated with the same model. And the same happened for Model B. You see, we go from ground measured data that tells us that soiling is as high as 4% to satellite derived particulate matter data that lead us to an estimation of 10.5% loss. So again, models have to be refined, and the community has really to be careful about which type of data they're using. So what I'm trying to do with my current project, Sole for PV, soiling live estimation for photovoltaics, is try to increase the accuracy of mapping soiling and try to provide also more information on cleaning recommendations. So again, I'm trying to move away from using PV power data and rather trying to estimate the soiling loss profile and the energy yield from environmental parameter in a similar manner to what I've shown. Also, I am trying to add additional parameters to the analysis, such as inverter saturation, anti-soiling coatings that will play a role in soiling mitigation. Unfortunately, we don't have time to go through those, but the idea is to move from a cleaning optimization model into a more comprehensive soiling mitigation model. So just to conclude, soiling has a significant impact on PV system worldwide, but likely we can mitigate it through, for example, cleaning optimization, which has to be run taking into account the cost of cleaning, the electricity price, but also has to be accounted for not only during the operation of the system, but even before the PV plant is operational. So thank all of you for your attention. I'm sorry if I've been slightly long, but I really hope you found the presentation useful. Thank you.
Thank you very much, Dr. Leonardo. Thank you, Dr. Greg Smestad. First of all, congratulations that you have made two talks which are very well related. That the first talk is very necessary to understand a lot of issue in the second one. I think it's you have shown how important in terms of cost of photovoltaics, the kilowatt hour, and we have to take into consideration definitively the loss of kilowatt hour and of money due to the cleaning, etc. And all these modeling. I think the student should contact you if they want to work on this topic. I hope it's possible for you to do that. Now we can open for the discussion. There are already some questions in the chat, and I think Greg have already answered to some of them. I don't know if we have to go back to these questions, but I rather prefer if the audience can ask directly now. So if someone want to ask, please open your micro. Ustad Salim will help you to open the micro if it's not possible, and we can discuss a little bit about this topic, which is extremely important for a country like Morocco, where we want to go to the energetic transition. By 2050, we want to have 54% capacity photovoltaics and CSP, etc. And therefore, without understanding the soiling and developing this technology of soiling and mitigation, etc., it's not possible, in my opinion, to get this target. So please, if you have any questions, the audience. So I have one question for, of course, both of you and for also the audience. Do you think that the other solution, which we don't use here, which is the super hydrophobic materials and self-cleaning, can be the best solution, or it's a very, very long-term topic which need more than 20 years or something like this? So what do you think about, or what is the status of this anti-soiling using materials, 10 films material, which can avoid the dust?
Leo, you want me to take that first or you?
Yeah,
sure.
go ahead. Go ahead.
Okay, so what we find, our colleague at NREL, for instance, and colleagues around the world are looking at anti-soiling and self-cleaning, which are two different types of coatings. In the first case, we can develop coatings which repel the soiling from the first case so that the soiling doesn't even deposit. In the second case, we can develop coatings that might help with the cleaning. And those are two really separate things. In the second case, the coating would help the water or some other way, once the particle is there, to get it off. And in the first case, the particle wouldn't deposit at all, even initially. Now, with both of these kinds of things, they're usually hydrophobic or hydrophilic coatings. And the way that people make those is to make porous films of silica, for instance, a little bit like the Grätzel cell, which was made of porous titanium dioxide. We can make porous SiO2 or silica, and this has properties of hydrophobic or hydrophilic, depending upon how you do it, and the water will run off in a certain way. Now, the problem with these coatings, which are also used as anti-reflection coatings, so I've mixed a lot of things up here, but these things work as anti-reflection coatings, and they work a little bit with anti-soiling or self-cleaning coatings, but they don't seem to function in the last two very well. And the reason why comes back to the reason why Leo and I are looking at the microscopy, which is that very soon the surface of the glass, either the surface of the PV module or the surface of a CSP mirror, it becomes coated with very tiny particles, sub 1 micron, even salt crystals. And this then prevents the surface properties from being what you think it would be, hydrophobic or hydrophilic. So Ahmed, you will really appreciate this because the anti-soiling coating is all about surface properties, surface energy. And unfortunately, a new coating of the very initial stages of the dirt changes those surface properties so they don't function well over time. So that's a long and complicated explanation of, yes, we have these coatings, but they don't seem to last in the way that we want them to for a sufficient length of time to really make a difference. And now we'll see what Leo says about this.
So yeah, thank you, Greg. So we are getting with anti-soiling coatings extremely nice results, in labs and indoor measurements and at initial stage. So I think right now the main concern related with this type of strategy is really durability. You have to think about a coating that is specifically made for your site. So the designer has to know, like, if your site is pretty exposed to dew formation, or, for example, exposed to wind, so that you can facilitate one or the other cleaning mechanism. On top of that, we are installing PV modules that are asked to work for 20, 25 years, 30 years. And so installers, investors are really worried about adding anything on the external, top of the PV modules, which might degrade quite fast. So I think durability is still the main issue with the, coatings and this type of strategy, because again, scratches might appear. And the risk is not only of losing the anti-soiling possibilities, but it's even to make the transmittance of the gas worse. So I think it's a very interesting topic. We know a lot, but really have to prove that those materials are able to withstand the 20, 25 years in the outdoor and in very harsh conditions.
Okay. Another question, which is very interesting, is if we add to your modeling another issue like agro-photovoltaics, we can say is okay, we need water, and this water we will not lose, we will use it for PV, for the agriculture. Do you think that this has can be topic for the future, that if we mix agriculture and photovoltaic, then we can decrease the price for both, for the cleaning, because we can clean more and we don't care because this water will be anyway used in agriculture, etc. What do you think about this?
Yeah, I completely agree with that. Especially as renewable energy researchers, we really care about sustainability in general, and clearly, making the best use, for example, of water will be key. And the integration of agri-PV and soiling will make it possible, probably, to limit the cost of soiling mitigation and limit the cost of agriculture together. So yeah, that can be a very good example of how these different activities might be beneficial from, might benefit from each other. So yeah, exactly. I think we are gonna see some, clearly there will be challenges, but there are also several benefits correlated, for example, with the installation of PV systems on the agricultural field.
Okay, thank you very much. And
thank you.
The audience, if there's any questions, we expect something from the audience. Is anyone has any questions? Please go ahead. So if not, then I would like to thank again Leonardo and Greg for this very nice talks, which we will have it in our web page, and everyone can see it again until if there are some issue you don't understand very much, you can go to the papers of both Greg and Leo, and if you need any help, just ask, and then we can help you. Thank you very much for this interesting webinar, and I hope to see you again on our virtual learning university.
Thank you, Professor Enoui. Thank you, Salem, for taking care of this webinar, for inviting us.
Just one information that next week, this means the 21, it's just the holiday for Ramadan. So that's Eid al-Fitr in Arabic. And therefore, we will not have any webinar. The next webinar will be in May, 5th of May. Yeah? That is for the PhD student and master student. So thank you very much. And Ustad Salem, do you have anything to add? Okay, then I think we will stop our webinar here. And if there is anything you want to say, Dr. Greg, Dr. Leonardo, before we close?
No, I just
thank. We both want to thank both you and Salem and the students, and again invite them to keep studying this topic and these topics in solar energy. There's a lot that you can contribute yourself to this, and we hope that you do. Leo?
No, I just, there was a question from Munir regarding the best model for clean optimization and if anyone comes up with questions, feel free to email either me, Greg, or ask for Professor Enoui for our contacts. We will be happy to answer any question that is still there.
Thank you very much.